Oh, it turned off on the machine on the next to the.
Oh, okay,
Yeah,
gotcha.
That's the problem. All right, so we're going to be talking about two things here. We're going to be looking at disturbance primarily, but we're also going to be talking a little bit about succession. And if you're tracking with the reading, which you should be, hopefully you were a little bit confused because you're paying attention to the details so well. But we're jumping around chapters because the story that we're telling in the class is a little bit different variation of the story that the textbook authors are telling. And so we are read Module 8 in Chapter 3, and this lecture is also going to be over Module 21, which is from Chapter 6, and then we're going to dive back and go back to Chapter 5, which we've already started in the previous, over the previous assessment. So we're kind of jumping around, but it fits with what we're going to be doing. So we're going to be focusing mostly on disruption today, the effect, the influence of disruption, focusing on the distinction between some key terms, which is resistance and resilience, looking at this central theory of ecology called the intermediate disturbance hypothesis, and looking at some case study examples, and then talking about ecological succession as a process for continued ecological productivity. So, just to keep our feet on the ground a little bit, this is a copy of sentence 3 of the narrative. The story that we're telling in this class is a 5-sentence story, exactly 100 words long. We did the first 2 sentences by the end of T1, and then we've just started into the 3rd sentence, and we're focusing right now on these underlined words. Organisms can respond to changes in the environment. What is it to change in the environment? But then we're going to move forward to thinking about survivability and what influences survivability. For this first part, I need 2 volunteers, if I can. Maria is one, and I need somebody else. Oh, Amara, front row, easy access to the stage. Come on up, girls. I'm going to give you this. I want you to watch and make some observations about what's happening. Come on up. You might as well, broadcast, We're going to repeat the narrative a few times. I need somebody who has quick access to their phone or a timer, and they're going to time what's going on here. We've got Catherine. Beautiful. All right. Maria, you're going to go first. We'll give Catherine a second to get this pulled up here.
Stopwatch?
That's perfect. All right, Maria, all you're going to do is just read through the narrative. You ready? Catherine, go when she starts.
Everything on Earth is highly interconnected with numerous natural systems that vary over space and time. Living organisms require both energy and resources, and therefore conversions in energy and matter underlie all ecological processes. Organisms can respond to changes in the environment, but survivability is dictated by biology and frequency and severity of disruption. Humans alter natural systems. Technology and population growth have enabled humans to increase the rate and scale of their environmental impact. Environmental problems have a cultural and social context. Understanding the role of cultural, social, and economic factors is vital to the development of sustainable solutions.
Stop. All right, perfectly done. Give Maria a hand. That's great, right? Got a great voice, great articulation. Such fantastic writing, Props go to the script writer. Now the same thing. We're going to get a baseline for both. So now time. Amara's going to read it. You got the time, right?
Yeah.
Oh, beautiful. Smart. Good scientist right there. Okay. Start when she goes.
Whenever you're ready.
Okay. Everything on Earth is highly interconnected with numerous natural systems that vary over space and time. Living organisms require both energy and resources, and therefore conversions in energy and matter underlie all ecological processes. Organisms can respond to changes in the environment, but survivability is dictated by biology and frequency and severity of disruption. Humans alter natural systems, technology, and population growth have enabled humans to increase the rate and scale of their environmental impact. Environmental problems have a cultural and social context. Understanding the role of cultural, social, and economic factors is vital to the development and sustainable solutions.
Stop. All right. I love science. We're doing a little science here today. This is a little experimental treatment. Unfortunately, you have to listen to the narrative a few times, but I figured if we're going to repeat anything a bunch of times in a row, it might as well be the narrative for our class. So this time we're just going to change it up a little bit, do a different style of treatment, experimental outcome, and the thing that we're quantifying is the amount of time reading for the narrative. So both of you, you're going to read again. Individually, we'll go one after the other, and don't change anything, just try to do the exact same thing you did last time, all right? say, okay, you ready, Catherine?
Yeah. Everything on Earth is highly interconnected. Technology and population growth have enabled humans to increase the rate and scale of their understanding the role of cultural, social, and economic factors as vital to development and sustainable solutions.
Stop. Let me try and mute the mics here. Oh, it went off. Okay, good. All right. Give Maria a hand. Pretty nice, right? Gotta love that. Okay. Now we're ready. Amara, it's your turn.
Everything on Earth is highly interconnected. With numerous natural systems that vary over space and time, living organisms require both energy and resources. Energy and matter underlie all ecological processes. Organisms can respond to change in the environment, but survivability is dictated by biology and frequency and severity of disruption. Humans alter natural systems. Technology and population growth have enabled humans to increase the rate and scale of their environmental impact. Environmental problems have a cultural and social context. Understanding the role of cultural, social, and economic factors is vital to the development of sustainable solutions.
Stop. Okay, great. Thank you, girls. You can take a seat now. Doesn't matter. Perfect. All right, thank you. All right, so this is an example. This is a metaphor of what we're talking about. In both cases, we had a process that was trying to proceed and naturally occur. In this case, it was a person reading through a 100-word statement. We're going to be relating this to ecological processes, which is the continued and increased productivity of ecosystems. The problem was there was a bit of interference, which is what we call a disturbance. Agreed? Fairly disruptive, very disturbing. Catherine, give me the times. How much longer did it take for Maria to read it the second time?
For Maria to read it, about 5 to 6 seconds.
About 5 or 6 seconds. So the impact of the disruption in this case, so all those things I was doing that were disruptive, delayed her process from continuing on its path by about 5 or 6 seconds. What about Amara?
She was 6.
She was about 6 seconds. So it delayed it essentially about the same amount of time in each case, but the disruption looked very different. This is going to be key, and we're going to use this to draw out a couple of the key definitions that exist here. So, changes in the environment. That comes from that underlying statement in sentence 3 of the narrative. That's what we're talking about. That is disruption. So anything that causes change in the environment is going to be a disruption. More specifically, ecosystems, this is the textbook definition, are affected differently by disturbance and how well they bounce back after disturbance. Both of those things are different. How well they bounce back and how they are affected by an individual disturbance event. Just like we could do the same thing with all people in this room, and they would all handle it in different ways. I would have lost it, my delay would have been much longer. Maria, outstanding stuff, right? So disturbance here is an event. It is caused physical, chemical, or biological agents in the environment. It's resulted in changes in the population size or community composition. Population size and community composition is kind of a fancier way of saying it's altered the biodiversity. It's changed the biodiversity and it's made it lower. It's reduced the biodiversity. And if you saw the title slide as you came in, higher biodiversity is always better. More productivity, the more biodiverse, the better the ecosystem health. Resistance is the ability of an ecosystem to resist change. So that is like Maria. So I was causing disruption, and I was messing around with her, but she was resisting it. She wanted to keep on her process, which was reading, and so she resisted all of the disruption. She narrowed her focus. She tried to keep on doing the task, trying to do it well. So that was a good example of resistance. In the environment, in an ecosystem, it looks very much the same way. It continues on, even though there's disruption or there's certain events. The ecosystem is able to push back because of its composition, and it's able to resist the influence or the impact of that. Resilience is the rate at which an ecosystem occurs after a major disruption has taken place. That's like what I did to Amara. So I removed, she tried to keep on her process, which was reading, but there was time lost for her to recover because I took the narrative and I threw it on the ground. So her process of reading was disrupted in the same way, and so the amount of time associated with her, between her resuming that and continuing on her productive process, that would be resilience. In an ecosystem, very much the same way. Again, when the disruption occurs and the ecosystem is affected, how long does it take it to get back to the state where it was before and resume on its productivity? Those both can be quantified scientifically in the same way. We use time here to quantify this exercise that we did, but ecologists can use different forms to do this and measure it and quantify it as well. These are not synonyms. So when you hear these words discussed in literature that you read, and especially as it relates to this class, or you hear these words spoken by me or Mr. Hopper or Ms. Metzger, or you see it on tests, they're not the same thing. Resistance is the ability for the environment to resist. Resilience is the amount of time associated with recovery. That leads us to this next theory, central to ecology. It's called the intermediate disturbance hypothesis. Focusing in on the disturbance piece right at the middle is, disturbance naturally occurs in the ecosystem, and it's going to cause some impact to biodiversity of the ecosystem. And so what we want to measure is, what is the impact of that type of disturbance? And what we see is that there's high biodiversity when there's an intermediate level, and by intermediate I mean both in terms of severity and in terms of frequency of disturbance. There's a sweet spot. So when there's no disruption in the ecosystem, unfortunately what occurs is the most competitive species that have a competitive advantage in that ecosystem outcompete all the other species. They dominate. And so species biodiversity goes down as a negative consequence. On the other side of the continuum, so if I'm looking at breaking down this graph now, species richness, or we can think about it as species biodiversity, low here near the origin, high here on the value axis, far away from the origin. When you're on this end with not very much disturbance, competition is, there's a few things that have outcompeted. The competition was not very high because certain things have already won. So the biodiversity is low. On the opposite side, if you have very frequent disturbance or very severe disturbance, it will also knock out all of the species, and biodiversity, unfortunately, will be low as well. When an ecosystem is at its best health is when the frequency and severity of disruption is somewhere in the middle between the two. It allows for competition to be high, lots of species are fighting and competing, and the biodiversity is very high at that point, at the apex. This is just a general line, and you can see here a general line, a trend line is drawn. It changes based on ecosystem and severity, but you always see this normal distribution trend. Here's the example from the textbook, and I like it because it's using a disruption. Most of the time we think about disruption being physical, but here's one that's just between two organisms. So in an aquatic ecosystem, the species biodiversity of richness when there's no disruption is really low. The best species are winning, they're the dominant species, so they're taking over. When we introduce this snail, the snail consume the algae, and what occurs is some of the more dominant ones, their populations are knocked back, and other species are starting to come in, so the biodiversity goes up. If the disturbance gets too high, in this case we have too many snails, then they're going to eat all of the algae, and the biodiversity is going to go down again. The disruption in this case is just too severe. So biodiversity of these aquatic algae are at the highest in the middle, in the intermediate point between the two. Beautiful. Here's a little case study that I wanted to do, and this is based on the disruption that's just recently occurred in California. I think most people know about it. It's been in the news a lot. 1,000 people, 1,000 plus people were missing. Over 70 people, unfortunately, passed away. There was a major disruption to the ecosystem as well. So even though the human tragedy, which is important, I don't want to lose sight of that, has been the focus in the news, I just want to think about it because it's a current relevant example of a major disruption that occurred in this area. So this video I'm going to show, it has no audio. We're just going to watch it, and the aerial view is mostly on the neighborhoods because of the human focus, but you can see and imagine what the impact would be of the surrounding ecosystem around this area as well. And I want you to try to attempt to answer these 3 questions based on what you just learned. Rate the resistance and the resilience of the forest ecosystem that you see. And you should use specific examples. So when we give you a case study on an assessment, we don't want you to just speak generally about resistance and resilience or generally about anything. Use examples, and if you have clues from reading or observational pictures, you should use those as examples to enhance your answers. Identify 2 physical changes that occur, and then this is a typo. It should say, how do those changes from number 2, how do they affect the overall forest ecosystem based on the intermediate disturbance hypothesis? So we're going to go here. Let me just pull this up, a little timer. Hit these and go. Time, we're going to watch the video again. I'm just going to let it play so you have more opportunities for observations. But turn and talk about number 2 with the people around you. Turn and talk and come up to, there's a lot of examples for number 2. Go. Good about number 2, talk about number 3 a little bit, and then we'll try to get some answers together.
Number 3, we could say that well, I think it's what fossils and habitats. Like the surface of the land because it's migration.
All right. There are a lot of examples for number 2. I tried to do this myself, and I came up with quite a few answers. Let's try to get some of these out loud and just think about it together as a group. Once we do a little deep thought, I think you'll see how big of a, how interconnected all of these things are. Give me some examples that came out from number 2. Yeah.
Like we learned about in one of our earlier podcasts, obviously the communication system between trees.
The communication system between trees, that's good. What else? Yeah. Smoke and chemicals in the air. Another physical change on top of the one that we already see as a disruption, which is the fire. Yeah. Organisms will be displaced, so we can make some key inferences. This ecosystem looks dramatically different, and so the habitat destruction and the home for animals as well as plants has been destroyed. What else? What about biogeochemical cycles? Go with yours.
I was also going to say, like, building off what Palmer said, it's not losing their habitat, but it's losing their food source. Like, the grass needs burn.
Losing their food source, so our flow of energy has been disrupted. How does energy flow? What chemical provides energy flow through the ecosystem? We can use that as a launching point for biogeochemical cycles. Which of the biogeochemical cycles is associated with flow of energy? Yeah? Photosynthesis is the key component part of what process? What cycle? Carbon cycle, right? Carbon cycle has changed in many other ways. The trees, instead of the carbon being in the trees, is now in the atmosphere. All of the plants are dead. If there's no primary consumers, you're going to have no energy flow. The carbon cycle is disrupted. The nitrogen cycle is disrupted. Like Maria said, the root system, assimilation of nitrogen into plants, decomposition of living materials. All of these things have been altered by this disruption. Okay? So we see good examples of physical change, a disruption that occurs, and what some of the influence of what that change looks like. Well, let's continue on here. I want to move on to the next piece here. And I have one small pause that I wanted to take. We're going to talk about after disruption occurs, we have this ecological process known as succession, which is going to be what we'll talk about for the remaining part of our lecture. And I had a quote, and I wanted to mention this is a story, something that happened. Our definition of ecological succession is the predictable replacement of species over time. When I was in graduate school, I worked for this place called the Roe Bird Sanctuary, which was in Kearney, Nebraska, and they measure all kinds of things with birds in the area. But one of the most important migratory phenomena occur right in that area, and it was key to the foundation of the Roe Bird Sanctuary as an entity, and it was the migration of sandhill cranes. There are millions, about 3 to 5 million sandhill cranes that come through and nest in this small 30-mile area every year in the spring, and then they disperse all the way out across all of Canada. In the summer, they're all over Canada in the summer, in the winter, they're all over in Texas, all the way to Florida and California, but for 1 month they're in this one area, and people come from all over. While I was working there, do people know who Jane Goodall is? Well, people come from all over the world to see this phenomenon because when the cranes take off, there are so many birds, they block out the sun. And Jane Goodall came with some of her friends to record a documentary while she was there based on this phenomenon. I had the opportunity to meet her, and this is a signed copy of her book. And this quote is not from online, it's from when I met her. This is her name here, and she says, I was asking her about the disruption that was caused in ecosystems because I was studying snakes at the time, and I was getting increasingly worried about just the ability of ecosystems to recover. And she wrote that nature is unbelievably resilient, and so there's always reason for hope. And my reason for bringing that up, we're talking about resilience, and succession and recovery of disruption now, but at the time it was a short, like 5 to 10 second exchange, but it was something that kind of changed my life, and I just wanted to encourage people here, never miss an opportunity to be inspired, always be looking for opportunities for your life to be changed by someone or something. I don't know what that looks like for you, but this was one of the things that was deeply impactful for me. And then I went on and been interested in succession ever since. Let's talk about what succession is, though. There are two types of succession, and we're going to start here with primary succession. Primary succession occurs when there's a major disruption in an ecosystem, and that disruption is so severe that it knocks the ecosystem back several stages, all the way back to complete bare soil or rock. So there are no living organisms anymore in the ecosystem. The ecosystem, an area, has been totally disturbed all the way back. That is primary succession. So what you should associate is if the disruption is severe all the way to bare rock or soil, then the predictable replacement that occurs over time, which is succession, will be primary. So here, this continuum shows time. While I'm on this slide, I just want to show you, based on the intermediate disturbance hypothesis, here's a good example of a few dominant species that are living, and they've outcompeted everything else for light. The biodiversity of this ecosystem on this stage is low because they're restricting access to light for everything else. Likewise, after a very severe disruption, the ecosystem biodiversity is low way over here as well. It's the healthiest at probably what point on this continuum. So if you look at this, somebody give me which area they think is the most biodiverse. Will, what do you think?
The one's the most of the red image.
You think this one?
The one farthest here.
Way over here? This one is probably out-competing. There's only a few species. Where would biodiversity be the highest? It's very low here and here. Yeah?
One to the left, above the different
It's probably somewhere in this range. It's probably more like the perennial wildflowers and grasses, even though it doesn't look as, this looks like you can see a lot of different species, but there would be more in this area. So at the intermediate level of disturbance, that would be when this ecosystem is at its healthy. But primary succession is bare rock and soil. The first species that come back in and recolonize an area after major disruption are known as pioneer species. They love full access to sunshine. They're usually small primary producers and lichens. On the opposite side, the climax species are usually K-selected, not always, but typically, and they remain unchanged for very long periods, things like trees, large species of mammals, etc. So these two are showing the two species on the continuum of primary succession. Secondary succession, you'll notice these two pictures look really similar. This one's blown up a little bit because it's missing everything that was on the left here. This is the succession that occurs when the ecosystem is just knocked back a few stages. It goes from here back a couple, and so there's still some organisms there. So secondary succession is the succession that's associated with the disruption where you do not go back to bare rock and soil. I feel compelled to make sure that I call out this misconception because I see it commonly by students, and it's that primary succession happens first after a disruption and then secondary. That's not true. This is an either-or situation. After a disruption, it's either primary succession occurs or secondary succession occurs. What's the distinction? Well, if it goes all the way back to bare rock and soil, then it's primary. If not, then it's secondary. Make sense? All right. Last topic here, if we think about the succession process, it's influenced by a few key drivers. One that we're really familiar with and we've seen abundant examples. It's latitude, the climatological factors, the amount of solar insolation. We also know that latitude tells us a lot about access to precipitation. Those two things increase biodiversity. They'll increase the rate and speed at which succession occurs. Time, and by time I don't mean time since this disruption, time since the last disruption. So when we think about the intermediate disturbance hypothesis, how much time occurred, if I can quickly scan back here, between the last one will allow this process to take place, and will tell you if you're only going back a few stages or going back much further. So the severity and frequency of disruption matters a lot. So time is a major factor as well. The size of the habitat, generally larger habitat sizes can recover at faster rates, and succession can proceed quicker, and that's because there are more species, more niches, more opportunities for dispersion, etc. And then the last, which I'm not going to spend much time on now because we're going to do a lot of this on Friday when we look at island biogeography, but it's the distance from other communities. So the way succession occurs is new species have to come from somewhere. Where do they come from? They come from neighboring ecosystems. So the distance matters quite a bit as well. Last case study for today, I'm going to show a video from a news clip about the Mount St. Helens eruption, the volcano which occurred in 1980, late 1980, so about 37 years ago. And I want you to think about these things. This looks like a FRQ that you would see on our exam or an AP exam, and you need to think deeply about breaking down the different component parts and answering this fully. So this is a good opportunity to work on your strategic and analytical analysis skills. But we're going to watch this, and I want you to think about the severity of this disruption. Think about the impact this disruption has on biodiversity, short-term, medium-term, and long-term. Just a quick characterization after the disturbance, what type of succession is taking place, little identification, then identifying 2 pioneer species that are provided as examples, and trying to identify 1 climax species. Hold on. Here we go. My bad.
Mount St. Helens in Washington State is one of the most well-monitored volcanoes on the planet, and with good reason. It is still active, and more than 3 decades to the day after it launched a stunning and destructive display of lava and ash, it continues to transform a region and its ecology.